In this video, we prove that b minus a by 1 plus b square is less than tan inverse of b minus tan inverse of a, and which is further less than b minus a by 1 plus a square whenever b is greater than a and a is greater than 0. We'll be applying Lagrange mean value theorem, or in short LMVT. What does Lagrange mean value theorem says? If f is continuous on the closed interval a comma b, so we need to produce a continuous function in the closed interval a comma b, and f is differentiable on the open interval a comma b, then there exists a constant c, such that f dash c equal to fb minus fa divided by b minus a. Now we want to prove this inequality. You see that we got something like f of b minus f of a, but we want f of b minus f of a by b minus a. So this inequality is true if, let's divide throughout by b minus a. Observe that we are given that b is greater than a and a is greater than 0. So b minus a is positive quantity, and if we divide by positive quantity or if we multiply by positive quantity, the inequality remains unchanged. Once again, if we divide by b minus a, this inequality will not change. So let us divide by b minus a, so that is same as saying we are multiplying by 1 by b minus a, which is a positive quantity. We are multiplying by 1 by b minus a, so we are multiplying by a positive quantity. And we are multiplying by 1 by b minus a. Okay, so this inequality is true. If this is true, the converse is also true. We observe that we can cancel b minus a out. So this is true if, that is, 1 by 1 plus b square is less than 1 by 1 plus a square, and tan inverse of b minus tan inverse of a divided by b minus a lie in between. So we need to prove this. If we could prove this, then we are done. Now let's apply Lagrange mean value theorem. Let fx equal to tan inverse of x, comma, x is a real number. We can restrict it to be positive real number. Then, but we want to apply Lagrange mean value theorem. So instead of writing x is a real number, we can say that x belongs to the closed interval a comma b. We want to show that f is continuous on the closed interval a comma b, and closed interval a comma b makes sense because we are given b is greater than a. Is this function continuous? We know that fx equal to tan x is continuous. Fx equal to tan x is continuous. In fact, it is a bijective continuous function. From is continuous from minus pi by 2, comma pi by 2 to r. Its inverse, f inverse of x equal to tan inverse of x, is continuous on closed interval a comma b for a greater than 0. Obviously b has to be greater than a. It is continuous. Inverse function is continuous. So for applying Lagrange mean value theorem, we should make sure that function is continuous, and we got first point to be true. Tan inverse of x is continuous. That's right. Tan inverse of x is continuous on the closed interval a comma b for a greater than 0. What about differentiability? Tan inverse is differentiable on open interval a comma b. It is in fact differentiable throughout R, and you know that derivative of tan inverse of x is 1 by 1 plus x square. So by Lagrange mean value theorem, if a function is continuous on the closed interval and differentiable on the open interval, there exists a constant c such that f dash c equal to fb minus fa by b minus a. Once again, by Lagrange mean value theorem or LMVT, comma, there exists a constant c, there exists a constant c, comma, f dash of c equal to f of b minus f of a, f of b minus f of a divided by b minus a, and that c is greater than a and less than b. Alright, that is, we got f of b equal to tan inverse of b, f of a equal to tan inverse of a divided by b minus a equal to f dash of c. F dash of x, that is d dx of tan inverse of x at x equal to c. However, d dx of tan inverse of x equal to 1 by 1 plus x square. So we can say that 1 by 1 plus c square equal to tan inverse of b minus tan inverse of a divided by b minus a, and that constant c is greater than a, less than b. Okay, we got something like tan inverse of b minus tan inverse of a divided by b minus a. And we need the expression 1 by 1 plus b square and 1 by 1 plus a square. How can we get it? We got 1 by 1 plus c square. Since c is greater than a and less than b, and a and b are positive, we can square it to say that c square is greater than a square, and that is less than b square. Okay, but we want 1 plus c square. So we add 1 throughout. 1 plus a square is less than 1 plus c square, and that is less than 1 plus b square. But we want 1 by 1 plus c square in the denominator, so we reciprocal it. We know that if 4 is greater than 3, then 1 by 4 is less than 3. So if we reciprocate it, the inequality gets reversed. So we can say 1 by 1 plus c square is bigger than 1 by 1 plus b square. 1 by 4 is less than 1 by 3. Bigger number, reciprocal will be smaller. This number is smaller, so reciprocal will be bigger. So 1 by 1 plus a square will be bigger than 1 by 1 plus c square, and which will be bigger than 1 by 1 plus b square. 1 plus b square is bigger, so its reciprocal is small. Again, that is true for positive quantities. But we got 1 by 1 plus c square equal to tan inverse of b minus tan inverse of a divided by b minus a. So we conclude that 1 by 1 plus a square is greater than tan inverse of b minus tan inverse of a divided by b minus a, and that is greater than 1 by 1 plus b square. Of course, if you like, you can multiply the inequality to say that b minus a by 1 plus a square is greater than tan inverse of b minus tan inverse of a, and that is greater than b minus a by 1 plus b square. You may wonder, why do we need that a is to be positive, a to be greater than 0? We need it just at this step. If a is less than c and c is less than b, then a square is less than c square and c square is less than b square. If a were negative, then this inequality, the squaring may not be true.